When we think about code, our minds usually jump to syntax and logic and all those semicolons. But what if there's something way deeper going on? Today, we're going to peel back the layers and explore the real philosophy of programming. We're going to trace the incredible journey from a simple thought all the way to an instruction that a computer can actually follow. So, let's kick things off with a big idea, a question that changes everything. What if coding isn't really about the computer at all? What if, at its very core, it's about language, a really unique and powerful form of human expression? Just let that thought sit with you for a minute, because it's the key to this entire explainer. All right, here's our roadmap. First, we're going to start right inside the human mind to see where an idea even comes from. Then, we'll look at how language gives that idea shape. After that, we'll nail down what computing really is, uncover these two totally different ways of processing information, and finally, see how it all comes together so we can tell a machine what to do. Okay, first stop on our journey. Before you write a single line of code, before you even type anything, there's a spark, an idea. It all begins right here, in your mind, as a purely biological process. The source material we're looking at today gives this spark a name, Ego. Now, think of it like this. Before you even decide you want to build an app, you have this mental concept of what it does, right? That's Ego. It's the raw internal blueprint that exists before you ever write it down or tell a soul about it. So you've got this blueprint in your head. How you get it out into the world? Well, through language, of course. And this is where things get really interesting, because there's a massive difference between spoken language, which is great for abstract ideas, and written language. Written language uses concrete, physical symbols. And it's right there, that act of creating fixed symbols, that's the direct ancestor of all programming. Okay, so if written language is kind of the grandpa of code, how does it even function? I mean, it's not magic, right? Turns out any language is just a system, and it's a system built with a very specific set of tools that let us construct meaning. And according to our source, it all boils down to three fundamental tools. You've got E, which is all about structure. Then there's Aroto, which gives us logic. And finally, Itoka, which creates relationships between things. These three are the absolute bedrock for expressing any kind of complex thought. So, how do they all play together? Well, think about a simple sentence like, the house is big. The house, that's the structure, ahun. It's a physical thing you can touch. Big, that's the logic, aroto. It's an abstract idea, a quality. And that tiny little word is, that's the polarity, itoka. It's the glue, the bridge that connects the physical object to its abstract property. And just like that, you've created meaning. All right, so we've got the human thought part down, and we've got the language to express it. So what does any of this have to do with computers? To get that, we need to really truly define what computing is at its most basic level. Here's the formal definition from our source material, and I want you to notice one word in particular. Computing is the creation and manipulation of symbols. Not numbers, not letters, symbols. That, right there, is the crucial insight. And that's the absolute key. Forget about complex math or text processing for a second. At the very bottom of it all, a computer is just following a set of rules to manipulate symbols. That's it. It's a symbol game. Okay, get ready, because this next part is the real aha moment of this whole thing. If computing is just a game with symbols, it turns out there are two profoundly different ways to play that game. And once you see this difference, everything else just clicks into place. And it all boils down to a really simple question. How is it possible for an expression like y plus y to give you two completely different answers, depending on how you look at it? Let's find out. These are the two worlds. First, you've got the spatial process. This is purely physical. It only sees the shapes of the symbols and how they're arranged. To this process, 3 plus 3 is just gluing the symbol 3 next to another symbol 3. But then you have the temporal process. This one's abstract. It's logical. It understands that the symbol plus means you should apply the rule of addition to the values of the other symbols. And wow, here is where it just clicks. Let's say the symbol y represents 3. In a spatial operation, which just joins things together, y plus y becomes 33. Simple enough. But switch over to a temporal operation, where the plus symbol triggers a logical rule, and suddenly y plus y becomes 6. Look at that. Same input, same symbols, but totally different outcomes depending on which world of processing you're in. So what's the big deal here? Well, it's huge. In spatial processing, your output is just a reshuffling of the symbols you started with. Nothing new is ever created. But in temporal logical processing, you can create brand new symbols. That 6 and that 7 on the right, they weren't in the input anywhere. They were generated by an intangible rule, by pure logic. And that is where the real magic of computing comes from. Okay, let's bring this all home. We have human thoughts, we have a language system to express them, and we have these two incredibly powerful ways of processing symbols. So, how do we actually use all this to tell a machine what to do? Believe it or not, it all comes down to this super elegant and simple formula. A computer instruction has just two parts. The operation, that's the what to do part, like add or concatenate, and the operand, that's the what to do it to part, the data, the symbols themselves. But wait, why do we even have to give it instructions? Why can't the computer just figure it out? Well, that's because there is a universe of difference between us and the machine. We are biological beings. We have this built-in, innate grasp of language. A computer, it's just a tool. It's a material agency. It has no senses, no intuition, no understanding. At the end of the day, it's just a rock that we taught how to follow rules really, really fast. And that, right there, is the job of a programmer. You are the bridge. You are the translator. You take that initial human thought, that arrow, and you use a specialized, incredibly precise written language to give exact, unambiguous instructions to a tool that has absolutely no capacity for understanding on its own. Which leaves us with one last really deep thought to chew on. We've seen that computers are absolute masters at manipulating symbols. They can follow our logical and spatial rules with mind-boggling speed and accuracy. But after everything we've talked about, do they ever truly understand what they're doing? I'll leave you with that. What do you think?